Hi, and welcome to the next lecture unit in the lecture chapter on support vector machines. And in this lecture unit here, I will directly connect what we have learned until now, so the geometric interpretation of the SVM optimization problem, to our good friend, the principle of empirical risk minimization. Okay, so until now, we have motivated support vector machines mainly from a geometrical perspective. We wanted to maximize the safety margin, but this is really not completely true anymore when we move from the hard margin SVM to the soft margin SVM. And the problem is that the introduced new slack variables, these zeta i's, they're not really distances anymore, but we are now adding them up in our combined weighted objective function, where we add up the squared norm of our theta vector and then, well, the sum over all of these zeta slack variables or margin violations. And the thing is that it would make potentially sense if we use something like this here, so gamma times theta I, so that is actually the distance, the geometric distance by which an observation violates the margin. And I guess it's actually not a bad exercise maybe for you to prove that this is actually true, but we're not doing that, right? We're using the zeta i's directly, and this already indicates, partially at least, that transferring this geometric intuition from hard margin SVMs to soft margin SVMs in a certain sense has its limits. So we are kind of, over stretching this intuition here a little bit. But we had to do this in order to be able to work with the support vector machine on non-separable data, and surely we don't want to give that up. So fortunately, there is completely alternative interpretation of exactly the same formulas, of exactly the same optimization program. And this gives also rise to a very, very nice connection to general statistical learning theory. So we can simply interpret support vector machines as regularized empirical risk minimizers. So, and this is also not very hard to see. We could have started out from this interpretation in the beginning, but you will see that we will actually use a loss in the new formulation of the support vector machine, or in this ERM formulation, that is maybe not that intuitive, that we might have not constructed initially. So let's see how this looks like. So we derived this quadratic program here for the soft margin SVM. I discussed this now a couple of times in the previous units, so I won't go over this again here. So what I do want to discuss is how we can change this now. So you can see here our inequality constraints, right? So you have here basically the label times the score, and this is supposed to be larger than 1 minus the slack. So in the optimum, these inequalities here, they will hold with equality because we are minimizing the slack variables here in the objective. So if this would not hold with equality, we could basically shift it down some more. And the other thing we can notice is, so these inequalities here, they will hold with equality, so we can now kind of rearrange the whole thing for the zeta value. So zeta is going to be 1 minus the label times the score. Okay, but this here, this can never become negative because we also have these non-negativity constraints on the zeta i's. And what that basically tells us is if this guy here becomes larger than 1, so if the sign of the label and the prediction are the same, so we're not doing a mistake, we're classifying the point correctly, and we are also outside of the safety margin, then we do not get a bonus for that in our objective here, okay? So this can never happen. Then we basically, the whole reason that we introduced this here was that in such a case, we don't need the slack variable. And it's now possible to tie all of this together in a very, very compact formulation where we basically take this guy here and write it directly into the objective. And we have to modify this a little bit so we make sure that this can never become negative, or when it becomes negative, we basically cap it to 0. And this is what I've done down here. So I just copied down the squared norm, so the first term. In here, in the second part, I simply now rewrote the zeta i's with such a function L of the label and the score. And this function I'm now going to define like this. So if the label times the score is less than 1, then I'm going to use exactly this here. So 1 minus y times f. And if it's larger than 1, then I'm going to use 0. And you could have also written this down in this even more compact form here, where we compute the max of 1 minus y times f and 0. Yeah? So that just simply means if this guy here becomes negative, we don't return it anymore, we cap it to 0. And this is exactly what we discussed before, kind of a formulation of this. And I guess you can already see why I'm using this L function here, because I'm now going to interpret this here as a loss. And if you now look at this formula here that we just derived, so simply copy this over, there's no change, you can now see that this is obviously an L2 regularized empirical risk minimization. So you can see our loss here, and you can see our regularizer here, which is simply the ridge, so the L2. And so this we do know very well. This here, or more specifically this guy here, we haven't really encountered before. So apparently there's some y times f going on that we have seen a lot of times before. So this is basically our confidence score multiplied by the label. So if this is positive, we are classifying correctly. And the larger it is, the more confident we are that our correct classification, is good. And if this here is negative, then we're incorrect. And if it has a large absolute value, then we are confidently incorrect. So how about we now plot this guy so we can get a better understanding of how this loss function feels like. And actually looks like this here. So here it has this, so we're plotting this as usually for binary classification in y times f. Here is the area where we do correct classifications. Here is the area where we do incorrect classifications. This here is exactly the point where we have scores of 1. So we classify correctly and we lie exactly on the boundary of the safety margin. Here we are exactly on the separating hyperplane, and here we are on the wrong side of the margin, so to speak. And you can see that even for correct classifications that fall inside of our safety margin, on the correct side of the hyperplane, we do incur a certain loss here. And this is actually the reason that this loss here is non-zero, that we actually maximize the margin. And you see how this then is basically, here simply a linear function, right? I mean, you can see this also from the formula. And this loss function we call the Hinge loss. And the reason why we call it like that is simply because this shape here, this angle looks like a door hinge. And so this is now a very, very tight connection of support vector machines to empirical risk minimization, and it took us some time to kind of rewrite and change and transform the problems. We arrived at this formulation, but actually a lot of empirical risk minimization theory and theory about regularization was actually established when Vapnik co-invented the support vector machine in the beginning of the 90s. So in a certain sense, the theory behind the SVM kind of was, at least a larger part of the theoretical fundament of what we nowadays call empirical risk minimization. And the hinge loss has a certain nice, interesting property. So first of all, it's continuous. So here we have I've also compared here to this 0-1 loss, where we know that we cannot optimize this, right? This is not even continuous here at the 0. So we can basically show the resulting optimization problem, if you would plug that guy in here, would become fairly intractable. But the hinge loss is a bit nicer in that regard. It is continuous. It's also convex. You can also see that it's an upper bound here on this 0-1 loss. And in a certain sense, you can see this as the best upper convex relaxation of the 0-1. So if you want to have something that's an upper bound on the 0-1, but there's also convex, so I mean, you kind of have to go up here in a certain way. Maybe you want to also go up in a robust fashion, so you don't become too outlier sensitive. And then, from that perspective, potentially the hinge is actually this best upper convex relaxation of the 0-1. Now, this ERM interpretation that we just did, this does not require any geometric interpretation either of the loss or of the regularizer. This is very nice, and I think we have now connected this to a lot of theory that we already discussed here in the lecture, and it becomes now very easy to compare this model, which is a linear model. Until now we haven't kernelized the support vector machine, made it nonlinear. So for us at the moment here, this f is simply a linear scoring function. We have a certain loss here on top of this, and we have a certain regularizer on top of this. So we now have our hypothesis space defined, we have our loss function defined, and we have our regularizer defined. And we can now easily compare this to a lot of other models from machine learning and get a feeling for the differences. What is also very nice about this representation here, this is one line, right? This is a very compact form to define our convex optimization problem for the SVM. It's also very nice that it is indeed convex, and because of this convexity, and because we have here a linear function inside of a convex loss plus a convex regularizer, so the whole thing is going to be convex, and this means that every minimum that we find of this guy here is going to be a global minimum. So we don't have to worry about finding something that's suboptimal, and we don't have to worry about restarting the optimization and so on. And this was also for a very long time a reason why people actually preferred support vector machine related types of optimization problems. We have nowadays probably moved a bit away from this as everyone is doing deep learning, which where the error landscape doesn't have these nice properties, but this made the SVM actually quite popular for a very long time. In addition to all of the nice statistical learning theory. Another thing that we could also discuss is that this formulation here is not only a simple, convex, compact optimization problem, it's also only an objective function without constraints. So it's an unconstrained problem. So remember before when we looked at this guy here, and we also did the dual of that was still had constraints. So I guess you potentially already wondered, how am I ever going to optimize that? What's potential options do I have in terms of algorithms? Maybe you didn't know a single one that can, for example, optimize something like this here. This is possible, but it's not, I would say, as intuitive, or as I guess there are not so many standard techniques that you might know how to optimize this. So if you look at this guy here, this might look a lot easier to optimize, and in a certain sense it is. But you do have to be a little bit careful here so that you don't cheat yourself. So this is a very nice, compact, unconstrained formulation, but this L function here, that's not super simple, okay? So this L function, this is non-differentiable at that point, so at least you have to be aware of that. which means you probably have to use specialized techniques that take care of this non-differentiability here of the loss, so something like subgradient techniques. This is not super difficult to apply, and you will see this also later here in the course, that the algorithms can be basically defined on half a slide, and they are actually quite efficient. But I just wanted to mention that. Another side note, so we are not discussing kernelization here currently, but some literature actually claims that the primal problem here, either this formulation or this formulation, cannot easily be kernelized. And I mean, this is really what we want to do. We don't only want to use linear SVMs, we want to use nonlinear SVMs through kernelization. This is definitely possible. You can do this in the primal. There's a very well-known paper by Chappelle, which shows this. So don't believe that. If you see this somewhere in an older paper, you could also kernelize this here directly. We can now also, through this empirical risk minimization, discuss whether we can maybe introduce variants of the SVM. Sure, this is possible. We can now basically start to play around here with the regularizer, change that. For example, change this to the Lasso, introduce variable selection into the thing. I haven't discussed this here on the slides. What I have discussed is, for example, what happens if you change the loss function. And there's a couple of different variants of the SVM, which are very well known in the literature. So one example is, or maybe let's start with the plot down here. So again, you can see here the 0,1 loss. We discussed this before. You can see here in green the hinge loss. We also discussed this before. So if we now start to dislike this point of non-differentiability because we want to move to more standard optimizers like gradient descent types of techniques, or Newton or quasi-Newton types of techniques, maybe you want to change the loss function to kind of smooth out the problem. And as we know, in machine learning, we usually are not interested in completely perfectly solving our training set optimization problem. In a certain sense, this is anyway a surrogate for what happens on test set observations. So maybe it's not so bad if we use other types of losses. I mean, in a certain sense, we are always approximating this guy here potentially anyway, right? So we're not doing exactly the right thing in the first place. So this loss function here, the hinge loss, is not necessarily carved in stone. So how about we change this now to something that's numerically a bit more simple to handle? And one option would be to simply square this term here. Then you get this smoother squared hinge loss, which I have to search a little bit here, is this gray guy. So you can not even differentiate this that much here from this Huber loss, where the Huber loss is basically also a smooth version of the hinge loss. You might have seen also the Huber loss before for regression, which started out with a quadratic part here in the middle and then had a linear extension. And this is exactly the same what we're doing here. The only difference is that after the margin point here, we don't go up, of course. We simply go on with a flat 0. And these functions are smooth, differentiable. We can now use more or less standard optimizers on them. You can actually, this least squares SVM here, the resulting optimization problem is highly connected to what we have to solve in rich regression. And you might remember this, that this for this case, for the rich regression, you only have to solve a linear system. So this holds also true for the least squares SVM, so you can solve that very, very efficiently. Problem is that all of these smoother losses that I'm discussing here do not really generate sparse solutions in terms of the data weights. So if you, I haven't written this here on the slides, but if you think about this dual problem, we had these alpha variables, and I said that many of these for the normal SVM with the hinge loss will become 0, right? So our solution at least in the dual, has a weight per data point. Our linear f function is a linear combination where the weights are these alphas, and many of them can become 0 for the SVM solution. This is what we call the sparsity of the solution. And for these smoother losses here, the sparsity will not happen. We will have always, basically with probability 1, we will have non-zero weights for all data points. So basically we have to store the whole data set in order to be able to form predictions. And this is this also usually has runtime implications, at least for the prediction. It also kind of removes this nice intuition of the support vector machines because we do not have support vectors anymore in such a case. Yeah, every data point is now active in our solution, and this is why some people actually dislike these types of losses, or there's a lot of extra research where people then still try to make these types of SVMs sparse. A final comment. So we could also, all of these losses here, the hinge, the Huberized hinge, the squared hinge, these are all new losses, right? I haven't discussed them before in the lecture, and they're all kind of extensions, variants of this hinge loss. So what we could also do is we could use a loss that we have already seen, right? We could use our good old friend, the log loss, or we could also call this Bernoulli or binomial loss. This is simply the loss that we have used in our logistic regression model. And if we do that, if we insert that loss here, you can see that there's also a close connection between the support vector machine and L2 regularized logistic regression. So in a certain sense, these are all linear models that we endow with a certain loss function, that we endow with a certain regularizer, and you can all kind of see them as one connected family with different statistical properties and different optimization properties. And this is why we like this general theory of hypothesis-based loss function regularizer so much, because it really helps us to contrast and compare models and see the connections between them.